kick off then? I'm going to talk about complexity, and in particular complexity in non-standard models of computation. So rather than standard Turing machines, that's things like quantum computers, quantum Turing machines, as we've seen about, mechanical computers and so on. I'll start by briefly recapping what we mean by complexity, what we mean by non-Turing computer, and go on to justify why we need to consider this topic in the first place. In other words, why we can't just apply what we know from the Turing machine about complexity theory to our non-Turing computers. And finally, I'll say a bit about how we can go about measuring the complexity of non-standard computers, and how we can make meaningful comparisons between these measurements. So the whole point of complexity is to measure the cost of performing a computation. And for our purposes, a computation can be thought of as evaluation of a function. So the user has some input value x, which is supplied to a computing system, and that provides an output value f of x. And that process consumes resource. Complexity theory is all about measuring that resource. And specifically, one thing that complexity theorists will be interested in is how resource scales. In other words, how much more resource we need to use to compute with larger and larger input values. So, for example, we might have a factorisation algorithm, and that might take more and more runtime as we start trying to factorise larger and larger values. So the resource we're considering there is runtime, but we could just as well consider the memory usage of the algorithm or similar. And different sorts of computer, different instances of different models of computation might use different resources. So, for example, we could consider the energy consumed in driving a mechanical computer, or similarly the energy required to get a desired wavelength in an optical computer, and so on. So complexity is all about measuring the cost of a computation. And the computation itself can take many different forms, and in my work I'm interested in the non-standard ones, things that aren't Turing machines, although things that may be quantum Turing machines. I'm not going to so much define what a non-Turing computer is. I don't think that's really necessary for this audience, but there's a few examples there on the screen, and also a few example problems that correspond to these things. So these are problems that the computers are either good at solving or were originally designed to solve or are famous for solving, and so on. Okay. One thing to note is that complexity theory has been developed primarily with Turing machines in mind, which is fair enough when you consider what real-world computation looks like. It'll typically be done by a digital computer which is running a program, and that program will implement some algorithm, and the algorithm is essentially a Turing machine. So by construction, complexity theory works very well for Turing machines. And what we'd hope is that it works equally well for non-standard computers. What we'd hope, in other words, is that we can take the tricks and techniques and tools of complexity theory as it exists for Turing machines and apply them to analyse the complexity of our non-standard computers, mechanical, chemical, optical computers and so on. But sadly it's not quite that easy. There are certain sorts of computation where if you just do a Turing machine style complexity analysis, it will miss the point of the complexity of that system. There are certain computers, certain computations that can be performed where other things need to be done. We're going to see one such computing system now. Okay. I'm not going to explain in full detail the system. The point isn't that you understand exactly how it was derived, exactly how it works. But I will at least give enough of a feel of it that we can perform a rudimentary complexity analysis of what's going on. So the system is an analog, almost optical computer for factorising. And so the problem we're given is that we have some n that we wish to factorise. Well, that's it. We have some n, we want to find its factors. And that problem has a geometric formulation which is closely followed in the implementation of the system. And that formulation says that we can consider the curve y equals n over x, which is on the screen there. And any point on that curve, any point x, y on that curve, is going to satisfy x times y equals n. So any integer point on that curve is going to have coordinates that are factors of n. So in this example, n equals 12, and we've got integer points at 1, 12 there, 2, 6, and 3, 4, and so on. And so we've restated the problem of factorisation as that of a search for points that are both on a curve and on a grid of points, on the lattice of integer points in the plane. And it turns out that this curve is a conic section. It can be expressed as the intersection of a cone in 3 space and the plane of the screen. So what we're actually looking for in trying to factorise some value n is the intersection points between a cone in 3 space and a lattice of integer grid points in the plane. And those two things, the cone and the grid, are what we implement in order to construct the system. And we implement them in such a way that their intersection can be identified. So I'll consider first the implementation of the grid. On the face of it, it looks like we're trying to implement an infinite thing. The grid points span the entire plane. They go off to infinity in all directions. But we only need to consider a finite subset of them. We're only interested in points whose coordinates are potentially factors of n. And factors of n fall in the range of 1 to n. So we only need to consider points whose coordinates, both x and y, are in the range 1 to n. And it makes implementation a bit cleaner if we consider the range 0 to n. So we only need to implement grid points within a finite square. Another simplification we can make is to note that there's some redundancy within these points. For example, this point here tells us that 12 equals 2 times 6, and this point here tells us that 12 equals 6 times 2. So having found one point, having identified the factors 2 and 6, we don't need the other point, it doesn't give us anything new. And more generally, by symmetry of where these points are and by commutativity and multiplication, we only need to consider half of that square. So we want to implement the grid points within that triangle. And another simplification we can make is to note that we don't need every single grid point in that region. We just need those green ones. And those are the points whose x and y coordinates have the same parity. X and y are either both even or both odd. And that's sufficient because we can assume that n, the number we're trying to factorise, is itself odd. If we want to factorise an even number, we can just iteratively divide by 2. That can be done efficiently in the Turing machine realm. That can be done on a digital computer, in other words, efficiently. And so, in having done all those halvings, we're left with an odd number that we can factorise as here. So, if we're assuming that n is odd, any pair of numbers, any pair of integers that multiply together to give n are themselves going to be odd, and so are going to be a green point. So these points here are what we're trying to implement as far as the grid is concerned. And we do that with a source of waves. We can think of these as electromagnetic radiation or similar. And some mirrors. There's a parabolic mirror at the top there and a couple of plane mirrors making a V shape. And that gives us, there's a couple of example rays that the radiation would follow. And we know that this vertical mirror here on the left reflects these rays back along themselves, and that gives us standing waves. And we can consider the interference pattern of all such standing waves within this triangular region. And what we find is that the maximal points, the points of maximal wave activity, are at these green sites. And if I go back a couple of slides, that's exactly the sort of pattern we're trying to implement to get our grid. So, we've used a source of waves and a few mirrors. That gives us an interference pattern within a triangular region, and the bright points, if we're talking about visible light, within that interference pattern model our integer points. So we have our grid, or at least the triangle of it that we're interested in. And we now want to implement the code. So we do that with another source of waves and a sensor. And the sensor lies on circular arc. The circle of which that sensor is part is a cross-section of the cone that we're trying to implement, and the source is the tip of the cone. So between them, that source and the sensor uniquely specify our cone. Explicitly, the cone consists of all the straight lines through the source and through a point on the circle of the sensor. And what we're interested in is where that cone, where those lines, cut through our triangular region. And by construction, by our choice of cone, by the fact that we've positioned the source and the sensor where we have, that intersection happens at this blue curve here, which is our conic section that we want to implement. It's our y equals n over x curve. So what we're looking at to get a factorisation of n, what we're looking for to get that factorisation, are points on that blue curve that happen to be in the green circles. We're looking for the integer points on that curve. And the way we can identify such points is by noting that, well, green points are the points of maximal wave activity in our interference pattern in the triangle. And so that maximal activity will maximally disrupt the radiation passing through from our source to the circular sensor. And that maximal disruption, as it passes through the triangular region, will result in maximal darkness at the sensor. What we're looking for then is dark points on the sensor. Having identified one, we can trace back and get just do a simple geometric calculation to get the coordinates of the point we're interested in. And the coordinates of that point give us the factors of n. So,
excuse me, how would you guarantee that there's interference between this source and, this maxima of the interference pattern in the grid?
It's a good question. It's a question of implementation. What I'm saying is sufficiently general that details of implementation aren't implicit in what I'm saying. It depends on how you implement things. For example, we could use water waves to implement our grid. So this grid source, way back here, this thing here, could be thought of as a source of waves. So the plane of the board, the plane of the screen, is the surface of some water. Here we have something regularly pounding that surface. And we have some barriers that stick up out of the water to reflect those waves. So from here we have concentric waves spreading out, then various reflections happen, and we end up with choppy water at the green sites and calm water in between. Then if we think of the second source, the cone source, as, say, visible light, what we get is that, so we've got our tray of water here, our triangular tray of water, we've got visible light coming from the source, we've got our sensor, so the source is above the tray of water, the sensor is beneath it, suitably positioned to allow for a bit of refraction. As light passes through a green point where the water is moving the most, that will result in flickering at the sensor, because the refraction will send the light either side of it'll oscillate over the sensor. Whereas if it goes through a still point, there'll be more light reaching the sensor. So if you average how much light you're getting over a wave cycle, a water wave cycle, then the dark points will correspond to the ones where the green points have been cut through by the radiation, by the light.
Okay.
So it depends on implementation. That's an example. And the general details that I've given here aren't enough to specify exactly how it will happen. So yeah, it's a question of implementation. So we have some way, depending on what sort of waves we're using, there will be some way, if we've chosen the wave suitably, of detecting these green points on our blue curve. The coordinates of such points will give us our factors. So a quick overview of the system, of how the system will be used. We first have to input n into our system, and that's done by setting certain physical parameters of the system that depend on n. For example, the wavelength of our first source, of our water wave source, depends on n. That wavelength is 2 over n. So that and parameters that similarly depend on n need to be set at the start of the computation. And our setting those parameters to encode n is our way of getting n into the system. Having done that, we then get the processing stage, which is where the waves propagate, they interfere, they produce the pattern of light and dark along our sensor. And then we get the output stage where we're looking for the dark spots in the sensor. We're doing a little bit of calculation to retrieve the coordinates of the points we're interested in, the integer points on our y equals n over x curve. In other words, to find the factors of n. And having spelt out that process, we can now start to think about the complexity of the system, specifically the time and space complexities of the system. So during the input stage, we need to do a bit of calculation. We have our given value n that we wish to factorise, and as I mentioned in the input stage up there, we need to do some calculations to find values to which we set input parameters. So for example, our wavelength of the water source is 2 over n. We need to calculate that value 2 over n, given n. And similarly for the other input parameters, we need to do a bit of calculation. But it's all simple calculations. It's divisions, multiplications, and I think there's a square root in there somewhere. But stuff that can be done efficiently by Turing machine. We can just use a digital computer to do this bit in time and space, polynomial in the size of n, the number of digits of the number we're trying to factorise. Similarly, in the output stage, we need to do a bit of calculation. Having measured the coordinates of a dark spot on the sensor, we need to do a bit of geometric calculation to retrieve the factors of n. But again, it's simple calculations. It's things that we can do efficiently, and in particular in polynomial time and space. Is that it?
So let's say n is about 2 to the 1000, which is a typical number you want to factor.
Yes.
Doesn't that mean you then have to, for example, manufacture the mirrors all to a precision of about 2 to the 1000?
Yes.
And you find lots and lots of spots that are almost dark, but not quite darkest, and they correspond to factors of numbers that are near.
This is the whole point of this talk.
Right.
Pretty sure it's in there.
So yes.
When you say constant time space, you don't mean including
Turing
time
machines.
used to manufacture this machine. Right?
That in itself is a constant overhead, because you can use the same apparatus to factorise any number. So the 3 mirrors and the source and everything else are fixed. All that changes are the input parameters, so that's things like wavelengths. In effect, what we're doing is manufacturing the curve y equals n over x. But rather than that getting bigger, and we're manufacturing that curve within the region 0 to n along each axis. But as n increases, rather than that square that we're considering getting larger, I'm keeping the same square and scaling everything down. So, as you say, there's then an issue of precision, in fact many issues of precision, in that we're dealing with ever more intricate things. The hand needs to be steadier in setting up the inputs, the eye needs to be keener in terms of getting the output out. So, the manufacture of the mirrors and so on is fixed. That is just a constant overhead, that's just a one-time thing, and then you've got your system. But because everything's getting more intricate and more finely positioned as n increases, there is certainly an issue of precision, which we're about to see. Okay. So, time and space complexity. These calculations in the input and output can be done efficiently, by which I mean polynomial time and space. Everything else is constant. So the rest of the input stage, the rest of the output stage, constant time and space, and notably the entirety of the processing stage happens in constant time and space.
Assuming your wavelength doesn't change with propagations.
Yes.
Because you keep the grid finite.
Yeah. So
depend on
there's a caveat on what sort of wave you use. So things like electromagnetic. I mean, there exist waves where that isn't a problem. So what we appear to have, in fact, what we do have is a factorisation system that works in polynomial time and space. And when you compare that to the traditional algorithmic types of factorisation system, the Turing machine for digital computer solutions, that seems a lot better, because with the algorithms you would have exponential runtime rather than polynomial as we have here. So it all seems too good to be true. And while what I've said is true, it's not the full picture. The catch is that we've considered time and space. We've considered the time and space complexities of this system. And we've got the impression from that it's a good system, that it's efficient, that it works very well. But the point is that we need to consider other things. And as you've already said, there's an issue of precision. Having just blindly done a Turing machine style complexity analysis of this system, having considered the Turing machine type measures, the time and the space, we haven't got the full complexity of the system. We haven't captured what's actually going on with this system. And another thing we should have considered is precision. For example, when we're doing the output process of the system, when we're measuring the dark spots on our sensor, we can consider how precisely we need to do that to get the right answer. It turns out that the precision with which we need to make those measurements, with which we need to measure those coordinates, increases as n increases, and worse than that, it increases exponentially. As we start adding more and more digits to the number we're trying to factorise, there's an exponential requirement of us to ever more precisely measure the position of these dark spots. And so we can think of precision as a resource that is required of us, that is used in the computation. And it's one that's increasing exponentially. It's where the problem with the system is. It's why we can't use this as a practicable system for factorising numbers. But nonetheless, it's a resource that we weren't considering when we did traditional complexity analysis. So the good news is, having noticed this problem, this shortcoming of complexity theory, the answer to the problem is pretty self-evident. I mean, the problem is that when we're thinking about the complexity of non-standard computers, for example, the analog system we've seen, we're not considering the right resources. The solution is simply to consider the right resources. That bit's simple. But that in itself presents a new problem, which is to do with comparison of systems. The whole point of measuring the complexity of a computing system is to work out how efficient that system is. We might have some non-standard computer that we've come up with to solve some problem. We might want to compare that with an existing digital computer that solves the same problem. We want to say which is the more efficient of those two systems. And now we've introduced all these new sorts of resource that we're considering. Now we're considering not only time and space and the traditional algorithmic things, but also things like energy and precision and so on. There are more things to compare. It's less obvious what we're supposed to be comparing with what in order to determine which of two systems is the more efficient. What we'd like to say is that for our digital computer, let's say time is the relevant resource, and for our quantum computer or whatever it is, that precision is the relevant resource. Having identified those relevant things, we can then compare those using big O notation and standard complexity tricks to say which system wins. So that's all well and good, as long as we can say what relevant means. As long as we know how to pick out which resource for any given system is the relevant one, or which resources are the relevant ones. And we formalise that notion of relevance with dominance. The formal definition's there, but the spirit of it is that the dominant resource is the one that overtakes all the others. It's the one that provides the asymptotically greatest contribution to the cost of the computation. So if we've got a system with polynomial time and space complexities, but let's say exponential precision, then the precision is going to dominate the others. And that's exactly what we saw with the factorization system. So using this, we can now work out what we're supposed to be comparing with what in order to say which of two computing systems is the better, in order to say whether our novel computer beats its Turing machine counterparts. So, what have we done? We've thought about complexity theory. We've noticed the bias to Turing machines, the understandable bias to Turing machines. But we've also noticed that it isn't too good at dealing with the complexity of non-standard computers. We've patched that up by noticing that the main problem is one of resource consideration. When trying to find the complexity of non-standard computers, we don't seem to be considering the right resources. The solution, consider the right resources. Then there's a slight issue with how to make comparisons between machines, and we've solved that with dominance. So what we can now do, using this extended framework of complexity, thinking in terms of additional resources and comparing in terms of dominance, we can make more informed measurements of the complexity of our non-standard systems. So that's about it. Thank you for your attention. I think we've got about 4 minutes before lunch for any questions.
And I'm curious how this sort of analysis would apply to soap bubbles. You mentioned the Blakey compute. Was it minimal spanning trees? Or?
Yeah, if you've got a couple of parallel plates joined by rods perpendicular to those plates, the rods represent vertices. So the problem that we're solving here is, given a set of vertices, join them up, you can make up your own edges, we're not restricted to existing edges in a graph. Join the vertices up with the minimal amount of pen. A way of solving that by physical computation is to take two parallel plates, have a bar for each vertex, join the two plates, dip it in soap solution, take it out, and then, because bubbles are trying to minimise their surface area, what you get is a minimal network.
Will it be a locally minimal network, or actually globally minimal?
There are no guarantees. There are the state.
Infinite time should be the global minimum.
Yeah, exactly. The state it wants to be is the global minimum. There are certain requirements of how the dunking is done and how it's all set up that affect the efficiency of travelling from local minimums, like getting it out of the local minimum and into the global thing we're looking for. And that in itself partly answers your question. The way it's set up, the ideal conditions that we're looking for aren't in fact attainable. The smaller the rod size that represents our vertex, the better, but it needs to exist. It needs to have positive thickness. So there are precision issues there. The more accurate, the better you want the system to be, the smaller and more precisely you need to set things up. For example, the rod thickness. So there are lots of places where precision issues creep into a physical system. I mean, I mentioned the reading of the dark spots in the sensor, but there are lots of other things we could have considered. And rod size is one in that example. But there will be, say, dozens of other places where precision issues will creep in. But usually what I found is that it's enough to just choose one carefully, analyse that one precision source, and what you usually find is that there's some sort of exponential overhead there. So that's really enough as far as complexity theorists are concerned. You don't need to then consider the other issues because you've already shown that it's a bad system.
Yeah, so this ingenious factorization algorithm that you have has at its heart the same kind of discrete Fourier transform computation that Shor is doing, right? I mean, it's not exactly the same algorithm.
It's not quite the same. The emphasis isn't really on finding the period of some repeating function.
No, I agree. I'm just saying there is a kind of discrete Fourier transform thing going on in the middle of it. So anyway, whether that's true or not is irrelevant. What I really wanted to ask is whether you could make a similar analysis of Shor's algorithm and critique the claim that it uses only polynomial resources.
You could certainly make the same sort of analysis. The resources involved wouldn't be exactly the same, I suspect. The point with quantum computation is that, certainly with the circuit model, you can analyse the complexity by counting the times that unitary transformations are applied, for example. You can count the gates that you're using, or at least the firings of gates.
But you still need precision in setting up that entangled state.
I get at least one email a year from someone like you pointing out this flaw. But if you look at Nielsen and Strong, they show that polynomial precision in the 2-qubit gates suffices. But yeah, because if you look at Shor's original paper, he sort of has the phase rotation of the roll exponentially small, and so every year, a couple of times a year, I get an email from someone. I have a 4-inch or something.
I see.
But naively, yeah, it looks like you need exponential precision.
There could always be something you can consider precision and then refute that, say that you may only need polynomial precision. But there is always something. I mean, with quantum computations, you can count the gates that are being used and you get something that's effectively runtime. The question then is that relevant? Is that capturing the complexity of the quantum system? And any use of entanglement of superposition is kind of introducing parallelism. That's the computational power. And any quantum measurements, any interaction of that sort with the system, in the fact that there are very sort of strict limitations on what you can measure, that introduces another source of what you'd like to think of as complexity. But in counting the gates in effectively measuring runtime, you're not capturing the amount of computation being done because of all this behind the scenes parallelism. You're not measuring the difficulty in doing the computation because of the measurement problems. And those sorts of things, the amount of computation being done and the difficulty in doing the computation, these things that we're not capturing are precisely the sorts of things we want to capture when we think about complexity. That's the point of doing complexity analysis. So even if you can consider precision and find out that that turns out to be polynomial, there will always be something, there will always be some way of thinking about computation that suggests that a certain resource will need to be considered. So yeah, you could do an analysis of Shor, for example, and depending on what sort of resources you were considering, you'd find different things.
This would be architecture dependent.
Yes, yeah. Certainly, I mean, if you're talking about a Turing machine, then there are certain resources that you consider. If you're talking about a certain implementation of a quantum system, then there will be other resources, different resources from the Turing case, that you would need to consider.
So what I'm wondering is, though, whether at the end of the day there isn't some ultimate resource like energy, or it's probably not energy, but something like low entropy. Because if I say I want to increase the precision of something, it's kind of the relative precision to everything else in the other one. So if I'm a physicist trying to build something, I'm going to use more energy or a bigger thing or something. And I wonder if not all the resources ultimately can sort of be brought back to just one, real. It's probably not energy, but something like low entropy. We're not in an equilibrium state, and maybe the ultimate computing resources is the sort of the low entropy regions of the universe.
Yeah, certainly a naive consideration of like just the sheer number of trade-off theorems that exist in complexity theory would suggest that, and there's an obvious trade-off between what I talked about precision and space complexity, in that the analog system is a fixed size. As you start using bigger n, you need to be more fiddly with how you're setting things up. Similarly, we could have made it that our scale, our size of a unit in the system stays the same, but as we start factoring larger n, the system needs to be bigger. So there's a direct trade-off there between what I call precision and what is space. And more generally in complexity theory, there are lots of such trade-off theorems that at least bound one resource in terms of another. So just a naive consideration, as I say, of the sheer prevalence of that sort of thing would suggest that behind the scenes there is perhaps a fundamental connection and perhaps even a fundamental resource that these are all facets of. I'll hopefully in the near future be able to answer that question a bit better, because what I'm starting to think about now is what is allowed to be a resource. Because at the moment, with existing complexity, you can take a Turing machine and you can count the time steps, and that's your runtime, that's your time complexity. You could equally consider the number of time steps, 2 to the power of the number of time steps. That would be another way of measuring runtime. It would be an unusual one, but it would certainly work. It would be internally consistent. It would be effectively the same sort of thing as counting the time steps. You're just labelling your numbers differently. So instead of having time steps, instead of having numbers of time steps, 0, 1, 2, 3 and so on, you'd have 1, 2, 4, 8 and so on. You're just calling your numbers something different. Now that's fine when considered in isolation, but when you start using dominance to compare different resources, you can then fix it so that you can prove anything. You could have a system, for example, that uses fewer space cells than it does time steps. But you could instead consider 2 to the s, 2 to the number of space cells, and that would be more than the number of time steps that the computation uses. So by just applying some function, for example 2 to the power of, to give yourself a new resource, a new way of measuring the resource, you can fix which one appears to dominate the other. So in using the ideas of dominance, you need to be careful about what you're allowing to be a resource. And that's what I'm looking into. My hunch is that a resource should have nice regular intervals as to what number you're allowed to measure. So for example, the number of time steps could be 0, 1, 2, 3, you can get any natural number. Whereas if you were saying 2 to the number of time steps, you could only get the powers of 2. And I think the criterion boils down to regularity of the spacings between the numbers that you can actually attain. That would seem...
I think I'd be looking for something more like the sort of fungibility, the polynomial things, you know, you now have polynomial subroutines, everything can sort of be concatenated and remain polynomial, whereas with those exponential examples, it's not clear that that's true. That seems to me what makes so useful in practice.
But as I say, in the near future, I might have more of an idea of what is allowed to be a resource, and given some axioms as to what a resource can do, which would take as their inspiration Bloom's axioms from existing complexity theory, but add these other things. Given that, it might point the way to some more fundamental, general resource behind the scenes. So, possible. Yes?
So I'm not sure if I understood this last exchange completely, but it seemed to me that you were suggesting or hinting at the idea that all resources are fungible for some universal resource like time. So presumably, when you formalize exactly what things are allowed as resources, you'd like to prove some sort of theorem that says whatever my dominant resource is, I can simulate that with, so if my dominant resource is being used exponentially, then I can simulate that with exponential time on a classical machine. Is that the kind of thing you can prove?
That would be one consequence of the existence of some sort of general overall resource, yeah. And certainly that would be a good way of then measuring for any given system how much of that resource is being used, and a way of making comparisons. But, yeah. Any more, or is it lunchtime?
I think it is lunchtime. Maybe other questions can be asked during lunch.
Yeah.
We should be reconvening then at, if I read this correctly, at 2 o'clock for the short talks.
Yeah, may I ask the people who speak this afternoon to put their talks on the computer?
That's the...